Hey guys, Buildzoid here, and unfortunately we are still on the topic of freaking power connectors. Yeah, I know. Um, but under the previous video, I noticed a few comments that made it seem like achieving good power balance on a card is way more complicated than it actually is. So today we're going to take a look at how some GPUs achieve power balance between their multiple 8-pin power connectors, or don't. We do have one example of doesn't. Um, but anyway, we're starting off with Vega, and the reason I chose Vega is because this is a very simple voltage regulator design in terms of just like how it's wired up. Um, and so the Vega has two 8-pin power connectors and, of course, the PCIe slot, right? So as far as I know, or yeah, if I remember correctly, the 12-volt power limit for the PCIe slot is 66 watts, and the power limit for these two is 150 watts each, right? So the maximum 12-volt power that the card can pull is 366 watts. The other 9 watts of the 375 are on the 3.3 volts, and we're just not going to concern ourselves with that because that is a low power rail, and yeah, we're just not going to worry about it. Um, Anyway, so how does this card achieve good power balance between its two 8-pin power connectors and the PCIe slot, right? So like makes sure that it doesn't pull more than 66 watts over here and makes sure that it doesn't pull up more than 150 watts on each of these. Well, that's really simple. So each of these 8-pin power connectors has a input filtering inductor associated with it, right? So like this one connects to this input filtering inductor, this one connects to this input filtering inductor, and then these input filtering inductors connect to the voltage regulators on the board. And so on this Vega, this portion of the vCore VRM, which is made up of 6 phases, 1, 2, 3, 4, 4, 5, 6, is connected to this inductor, which means it is always connected to this 8-pin. It literally, like, if you do not plug this in, this part of like this voltage regulator just doesn't have power at all, right? Um, and cannot function, and therefore the card will not turn on because yeah, there's no power for that. And then this inductor powers the other 6 phases, making up the vCore voltage regulator, right? So that's again 1, 2, 3, 4, 5, 6. And so that's just connected to over there. And then the HBM power delivery is wired to the PCIe slot, which technically goes through this input filtering inductor over here. So like this is wired to there. And then these voltage regulators over here are also wired to here. And so basically during the design phase of this card, the designers basically went, okay, our core power limit is or like core input power limit, and this isn't the actual power limit of this card, this is just numbers for my convenience, is 288 watts, right? And 288 watts, let's say we're 1.2 volts output voltage. So that's going to be, now you're going to see why I went with 288, because I do remember 12 squared. So basically we have 140 watts coming in down this line, 144 watts coming in this way, right? And then that's 120 amps out at 1.2 volts. We're ignoring the fact that the voltage regulator has some efficiency losses. And then up here we have 120 amps at 1.2 volts. So that's going to be also 144 watts coming in. And so the card will not overdraw either of the two 8-pin power connectors because, yeah, each of these, like the VRM has a combined 280 watt power limit. And so, uh, you know, and half the VRM runs off of one connector, the other half runs off of the other connector. As long as the current flowing through all of the phases is reasonably well balanced, which it should be for optimal efficiency, by default, the voltage like the controller for the VRM is going to be doing its best to maintain even current distribution across all of the phases because that achieves optimal efficiency. So basically, under normal operation, you should see something like 20 amps flowing through every single phase. Um, right? So you get something like this, and as long as the current balance, like as long as the VRM itself is current balance, which is the like operating goal of the voltage regulator, right? It basically has two goals: achieve the desired output voltage and even current distribution through the phases. because the even current distribution achieves good efficiency, and 1.2 volts is the desired operating voltage of the GPU. And so as long as the voltage regulator is doing a good job, the two power connectors are going to not be overloaded and balanced. And then the HBM simply doesn't pull that much power. I think it like outputs somewhere between 20 and 30 watts at most. And these voltage regulators over here are like, I don't know, like a watt each. So like, well, okay, maybe not a watt, but these are very low power. Um, so yeah, we just shove all of the low power voltage regulators onto the PCIe slot because they're never going to pull more than 66 watts even combined together. Like all of these, so basically the designer of this card during the design phase just had to measure how much power this needs, how much power this needs, and add that together and go like, okay, that's less than 66 watts, so we're just going to shove that on the PCIe slot. And then the two big power rails, we shove them onto the 8 pins and we're good. The card is never gonna is not gonna be overdrawing. Like under most circumstances, it will not be overdrawing either of the power connectors. Like one potential issue with this setup is that during big transients, you can sometimes end up with some phases just ending up pulling more current than the others for a bit. Right? So you might like suddenly get like 30 amps on this phase. And then here we'll have like 130 amps instead of 120. And that will end up, will it end up overdrawing? Okay, so it'll briefly like overdraw one of the power connectors before the voltage regulator has enough time to rebalance all of the phases again. But it's not really that big a deal, right? Like, it's not really a big problem. These power connectors have huge safety margins on them, so slightly overdrawing them for, a few milliseconds doesn't really matter. So that's how Vega achieves power balance. And for comparison, here's a 2080 Strix. Oh boy. Now there's a reason I went with Vega and the 2080. So if we go look at TechPowerUp's review of these cards, you will see that the 2080, maxes out at 270 watts. The Vega maxes out at 362 watts. So yeah, it's still within the power limit of the PCIe slot and the two 8 pins. So the Vega pulls way more power when running FurMark than the 2080 does, and it also has way simpler power balancing than the 2080 does. Because NVIDIA is just insane, is the only explanation I can come up with. So let's take a look at how NVIDIA intends for a 2080's power distribution to be handled. Oh, I'm on the wrong... Wait, oh, I've got the wrong color. Oops. Anyway, so again, we've got two 8 pins. That's the other reason I went, right? Two 8 pins, PCIe slot. So you'd think, okay, we got a 2-phase memory VRM up here. So, the lazy way would be like, oh, we just put one memory phase on one 8 pin, the other memory phase on the other 8 pin. Solved, balanced. We don't, we don't have to worry about this anymore. And then the vCore VRM is a 10-phase. Actually, I should have just highlighted the whole block. Actually, I'm not sure why I'm covering the capacitors. Those aren't actually important. So, right, we got 1, 2, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And so you might think like, okay, the lazy way of dealing with this is just split it down the middle, shove one on the 1 8 pin and shove the other on the other 8 pin. We're good. And at this point, you might be like, okay, well, maybe we might have a bit of an issue. Like, we're not really using the PCIe slot for anything. So, I don't know, maybe we'll shove the entire memory rail on there. It depends, right? Yeah, so that would be like this. If this card was wired this way, this would basically be the same thing that the Vega does. The card is, of course, not wired this way because that would be too easy. You might notice we have a bunch of random MOSFETs scattered around the back of the card. Oh, and a lot of extra shunt resistors. Right, we have the main ones. Oh, this one for the PCIe slot down here. But then we have these 3 extra ones. That's concerning. Why are those necessary? You only have 3 power inputs. Why do you need 6 shunt resistors? Well, you see. This is an NVIDIA card. And if you look at the back of the board, what you will notice, and what I find kind of horrifying, is there are 12. I mean, not 12. There are 5 different 12-volt regions for just the vCore VRM. We have one over here, one over here, one over here, and one over here, and the last one up here. This one is for 2 power stages, this one is for 2 power stages, this one is for 3 power stages, this one is for 2 power stages, and this one is for 1 power stage. This is a reasonable way of doing your 12-volt power distribution on a GPU, if you're really bored. Oh, we've also got more MOSFETs on the back here for shuffling 12-volt power distribution around the board. Amazing. Truly, like, necessary circuitry on a card that doesn't even pull more than 300 watts. You know, like... But anyway, so what's actually going on over here is that this runs off of the slot. This set of power stages is hooked up to this bank of MOSFETs over here and this little input filtering inductor. So these are basically like on flex power delivery, where these MOSFETs, and there's 2 more on the back, these are basically used for changing where the power comes from. So I'm assuming like 2 of these are probably connected over here, 2 of these are probably connected over here, and the 2 on the back might be connected to over there. Or actually, I probably got that backwards. It would probably make more sense for these 2 to connect to here. But I'm not sure because, yeah, like multi-layer PCB and, you know, there's just kind of stuff everywhere. Anyway, then we have the 3 power stages over here, which are hooked up to this. And for some reason, we have a shunt resistor, and what I'm really hoping that's not actually connected to that, because that's more MOSFETs. Then, of course, we have this part over here, which is connected to another one of these, like, flex MOSFET arrangements. Oh, there we got more. Like, oh, of course, the shunt resistor. It's just like, why? Right? Like, there's so many lazy ways of wiring this that wouldn't involve any of this. Like, let's say, like, one potential issue you might have if you wanted to split it right down the middle like this is that, maybe these 2 power stages share a PWM signal, and so that would cause problems, right? Like if maybe this power, like maybe you'd have like 11.98 volts over here and 11.985 over here. So that might cause some kind of issues, maybe because you know, like these 2 power stages have the same turn on time because they're on the same PWM signal, but the voltage coming into them is different, so the current balance on them might go out of whack. Probably not ideal. So, you know, in that scenario, you know what else you could do? You could just lop these 2 off, split it like this, tie these 2 permanently to the PCIe slot, these over here, and then this over here, and this over there. And, like, you know, assuming that this VRM has, say, I don't know, a 240 watt power limit, this would still be 48 watts down here. Or you could just build the VRM, you know, like all of that cost that went into all of these extra, like, balancing MOSFETs and the controllers for that. Like, these things are stupid MOSFETs. You need like extra logic circuitry to like detect where, you know, you need like where to connect these MOSFETs to, like which MOSFETs to switch on and when. So it's not just the MOSFETs, oh, and the extra inductors and the extra shunt resistors. You also have extra controllers. And I'm pretty sure that if you added up all of these extra MOSFETs and all of these extra shunt, like the extra shunts, the extra MOSFETs, the extra controllers, you know, add that all together, you could probably buy 2 more power stages. So just make it a 12, split it right down the middle, and do the same thing the Vega did. Simple. Or you could do something like, I don't know, you split it like this, put one on the 8-pin, one on the other 8-pin, and so, yeah, one of the 8-pins might be running like 140 watts and the other one 100, but then, you know, you could also split them, like maybe the memory VRM outputs like 50 like pulls in 50 watts, so you could just split this in half, 25 could go to the PCIe slot, and the other could go to this, and you'd pull this up to 125. Right? Like, there are dumb ways to wire this up that completely avoid the necessity of all of these silly current balancing circuits. But this is an NVIDIA card, and NVIDIA hates things that are simple and effective. And just to drive my point home about how all of this extra circuitry is completely unnecessary, here is an MSI 2080, which lacks all of that extra circuitry, because evidently MSI shares my opinion on the complete pointlessness of all of that extra circuitry. So how did MSI solve the problem? And funnily enough, this is a very similar vCore VRM to that Asus card, because it is also 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 power stages. So how did MSI solve this? Well, this power stage is always wired to this inductor, which basically goes like this, through the shunt resistor, through the fuse, and to the PCIe slot. Oh, also these voltage regulators over here also run off of the PCIe slot. And then these two memory phases, one of them runs off of the PCIe slot, the other one runs off of the 8-pin. So, and you can see that on the back of the card, which is how I know. Technically, I also actually own one of these cards, so I could have measured this, but like, I have eyes. We can clearly see this bridge resistor right here. So yeah, this is 8-pin slot, and then, you know, we've got slot. And at a glance, this actually looks kind of wacky like the Asus card, because like, the hell is this? Why is there 3 different 12-volt polygons behind our power stages? Well, that's actually very simple. This is bridged to this. So if we look at the front of the card, we got this bridge resistor over here. So these 5 are together. These 4 are together. And so, yeah, MSI basically did what I, well, actually, no, this is a bit different from what I suggested. But so you have this one runs off of the PCIe slot. You've got these 4, which run off of one of the 8 pins. And I'm guessing it's going to be the same 8 pin as this memory phase, because we've got 5 power stages up here that probably run off of the other 8 pin. No extra current balancing circuitry whatsoever. Why? Because MSI didn't want to pay for it, and because it's stupid. So, you know, if you look at the back of that MSI card, you actually can see all of the missing current balancing circuitry. Because, yeah, it is stupid. Look at all of these MOSFETs that we don't need because they're useless and pointless and a waste of board space. But NVIDIA insists on having these. Like, the reference card, the reason I'm not using the NVIDIA reference card for this video is because that board is so crammed full of just stuff that it's really hard to look at and highlight specific circuits. So, yeah, but this is like, I do not understand why, like, the 12, like, as far as I'm concerned, the whole, like, oh, the 12-volt high power connector doesn't require current balance, like, doesn't, because when I say current balancing, I guess you could sort of distinguish between passive current balancing, where the board designer just measures how much power each of the power circuits needs to pull, and then just wires them in such a way that, you know, they achieve current balance. And then you have the insanity that is the active current balancing that NVIDIA, for some reason, has on some of their cards. And, like, I don't want active current balancing. This is unnecessary. This is a waste of board space. It adds cost and complexity. The only good thing about these MOSFETs, in my opinion, is that sometimes when a power stage fails, these act as fuses. Because the power stage, like, is capable of dissipating more short circuit current than these are. So if you have, like, a dead, like, and I've literally experienced this with an Asus Strix card. It had a dead power stage, and that dead power stage burnt the crap out of some of the current balancing MOSFETs. Because it pulled so much current through the current balancing MOSFETs that it just burnt them out first. Which did mean that desoldering the power stage was really easy, as it didn't get enough energy to weld itself to the board. But, yeah, like, you know, instead of using crappy MOSFETs as fuses, maybe we could just use actual fuses. Which, again, MSI also did on this card. You have fuses on this thing. Amazing. I mean, to be fair, I'm pretty sure you could have the fuses even with the active current balancing circuitry, but I don't think the active current balancing circuitry does anything, or it doesn't do anything useful. Um, Now, I guess one thing that I should point out is that the MSI card does basically not have a power limit, because, yeah, when you run firmware on it, it apparently pulls up to 363 watts, but it is still not violating the spec of a dual 8-pin power card, so I fail to see the issue, right? And under normal gaming operation, it behaves basically the same as the Asus card does, except that it has a somewhat higher power limit, which, if you're an overclocker, is actually just a good thing, right? Because it has more headroom. Well, actually, from the stock factory configuration from MSI, it has less headroom because the card is power throttling less out of the box than the Asus card is. But, um, like, I fail to see the issue, right? Like, yeah, I don't see so basically when I say GPUs, when I say cards should just power balance the 12-volt high power connector, I don't mean we need to go to the insanity that was the 20 series NVIDIA cards, or even the 30 series cards. Like, the 30 series cards basically have all of that same... Actually, I don't think they have quite as much. But yeah, 30 series cards also don't exactly have the most reasonable power distribution wiring on them either. But we don't need to go to that. We can just go to what every AMD GPU ever did. Even 9070 XTs, which, as of recently have a bunch of shunt resistors on them, just wire, like, if you have a dual 8-pin 9070 XT, half the card runs off of one 8-pin, the other half of the card runs off of the other 8-pin, and all of the really low power voltage regulators run off of the PCIe slot. This isn't really that difficult. You don't require any active components, you just need to wire the card in a way that makes sense. And NVIDIA just refuses to do that. So, yeah. And that's the thing with the 12-volt high power connector is, like, it would be really simple to me. Like, we have, like, a 600-watt power connector, and that power connector has 6 pins on it. So, as the board designer, right, it's like each pin effectively has a 100-watt power limit, right? And so as the board designer, I can be like, well, my card isn't super high power draw, so I'll just combine these two and just go like 100 watts into each, right? And I'm never at any risk of overloading the connector or ending up in a situation, because the current situation is that all of these get combined and your 200-watt card pulls 200 watts from from the whole thing combined. But then if something goes wrong on this side, right, that 200 watts is going to come in through just one pin potentially. Whereas on, like, cards with multiple 8 pins, that just doesn't happen. I mean, unless we take a look at this ASRock GPU, because ASRock decided that even just hardwiring the 8 pins in a way that makes sense was apparently too much design work for them, so they just combined all of them. Which I am not very much... Yeah, I'm not really a fan of this. The other downside to doing this is that it makes fusing the card basically impossible, because with the MSI setup, right, on this card, you can have like one 20-amp fuse for a set of power stages, right? So even if something went really wrong here, that fuse is going to blow if the card tries to pull more than like 240 watts through that channel. Yeah, if you just combine all of your 8 pins like ASRock did here, you now need like a 60 amp fuse, which that's just not useful anymore. That's just not going to protect anything. Like, the power supply's overcurrent protection is probably going to trip before that fuse is going to blow. And actually, some power supplies might actually die before that fuse blows. So, yeah. I am not a fan of having one giant 12-volt power rail. Just in general. Like, honestly, I think it would even... Like, with motherboards, it's different because you do have just the single 8-pin usually, and you don't usually have devices that, like, even these days with high power draw CPUs, they're usually up to like 300 watts. Whereas GPUs are now going regularly over 300. And personally, I would still appreciate if motherboards did have fuses for their power delivery, because that is a thing that can happen where, like, a motherboard's power delivery fails and then it kills the CPU. Anyway, And that's like also the same reason why I like fuses on GPUs, is because the fuse, it's not going to prevent a failure, it minimizes damage. But that's not the point of this video. The point of this video is that power balancing your connectors is not that complicated. You can literally just hardwire them. Right? And so with the 12-volt high power connector, like, I really don't see a reason why the spec doesn't just put the... Because the spec, as far as I know, literally requires that you combine all of these together. I don't really see a reason why the spec doesn't just put the balancing requirements onto the board designer, right? Because it's like, okay, I might have a 200-watt V-core, and let's take an AMD card because those can be wacky. Then we have like a 20-watt sock rail, right? So VSOC, 20-watt, 10-watt memory controller. So that would be VDDCI. Then let's say 30 watts for the memory. So MEM, right? And so I've got all of these different power rails, and added up, this is a 260 watt GPU. And it's like, okay, so I want to wire this into there. And it's like, okay, so I could group these two together, put them on, like we could do like, because each of the pins is a 100-watt power limit effectively, right? So you could do something like that, split this in half, so you get like two 100-watt rails, and run one here, run one here. So the V-Core VRM could be like an 8-phase, which would actually, or like an 8-power stage, not an 8-phase, because technically the V-Core VRM on a 9070 XT is a 4-phase, but it has 8 power stages in it, but that doesn't matter. But you just need a number divisible by 2, basically. All right, and then you could go like, okay, this 20 watts. Actually, yeah, we could group these two together, put those on one of those, and group this, like put just this onto there. Balance has been achieved. And if you want to get even fancier with it, you could potentially do something like... this, where you group all of this together, shove that on there, then put 100 watts of V-Core over here and 100 watts of V-Core on the other two pins, right? And worst case scenario, like, yeah, this isn't perfectly balanced. You know, we're not using the power connector perfectly, but no two pins are at risk of being, like, no pin is at risk of being overloaded by more than 2x in this scenario, right? Because even if this got wrecked, and that got wrecked, and that got wrecked, we would still have one perfectly good 100-watt connection, and then 160-watt, right? So, like, and the funny thing is, like, for all intents and purposes, that's exactly what dual 8-pin cards did, or triple 8-pin cards do, right? Is you'd literally have this exact same scenario, and it's just like, okay, so we take 100 watts of V-Core, shove it into one 8-pin, the other 100 watts of V-Core we shove into the other 8-pin, and then actually in this case, like, this is a thing that I think when you first started seeing cards that had like an extra 6-pin, because it used to be like, for the longest time, you wouldn't get a card with more than 2 8-pins, right? And then for a little bit, we had some overclocking cards like the 290X Lightning, actually, I don't think the 290X Lightning did it, but I think 980 Ti Kingpin Edition was, I think, the first card to do this, where it had a 6-pin power connector as extra. That 6-pin power connector is literally just powering the memory VRM, if I remember correctly. So yeah, you could do like 100 watts of V-Core to one 8-pin, 100 watts of V-Core to the other 8-pin, and then your 60-watt everything else you could just shove into a 6-pin power connector, right? And if you wanted to be extra, you could just make this an 8-pin, because, like, that's ultimately why I think the 8-pin, like, triple 8-pin became a thing, is because the 6-pin connector and the 8-pin connector on most power supplies are the same thing. So it actually just doesn't matter if you use a 6-pin or an 8-pin at that point. Because, and this is one thing that kind of annoys me about the 6-pin and the 8-pin power connectors, is that what they're actually wired as is power, or like power, where this pin is optional, and then you have ground, sense, ground, And then the 8 pin is power, 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 ground, sense, ground, I think another sense, and then a ground up here, which is just like why did this could literally handle the same amount of power as this, right? But of course, as far as I know, the 6 pin is an NVIDIA design because NVIDIA, like Intel doesn't make GPU add-in cards. So I haven't checked this, but as far as I know, the 6 pin was either designed by NVIDIA or in collaboration with NVIDIA, and so a useless sense pin and then more useless sense pins would be the most NVIDIA thing I've ever seen. And it's worth pointing out the 12-volt high power connector has a bunch of useless sense pins on it. It's like if you look at the 8 pin for motherboards is, or the 8 pin and the 4 pin for motherboards is literally just power, power, ground, ground, and the higher power connector is just more power and more ground because yeah. And what's actually kind of, well, this is arguably one flaw of the EPS 8 pin connector is you can technically plug a 4 pin into this and it will turn on because there is no requirement for detecting if an 8 pin or a 4 pin is plugged in. It's just, but the thing is like we just assume that the end user is not an idiot in that scenario instead of designing a stupid power connector that's supposed to be idiot proof, right? Because that's the point of the sense pins is like, oh yeah, if you plug this into this, it doesn't register that sense pin and then it doesn't like turn on or well, the card will like not turn on or it'll turn on and tell you that you didn't plug in the correct power connector. And it's just like, but motherboards don't even bother with that. Like, or you could just have different, like fundamentally different pinouts for the connectors. Or what you could do is like, you know, with the N8 pin case over here, this could act as 2 separate 4 pins where this powers half the VRM. And so if you don't plug this in, the board can't turn on, right? You just do what the dual 8 pin cards do. And actually on that note, there are cards like some 6 pin power connector cards, which don't bother with the sense pin at all because they work on that assumption of like, well, if those 3 power pins aren't plugged in, the card can't turn on because there's no power. So, like, why do we need the sense pin? What does this even do? So, yeah, like, I can kind of understand why the 12-volt high power connector is like, oh, yeah, we're just going to combine all of the pins because it does simplify the board design. It also completely invalidates the ability to use fuses, or at least it makes using fuses way less convenient. Because the other, like with the multi 8 pin power connector cards, you just put a fuse per power connector and you're good, right? Like, doesn't really get any simpler than that. Whereas with the 12-volt high power connector, especially on NVIDIA cards, you're just screwed. Like, there's nothing you can do. As far as fusing goes, because the board itself at this point doesn't have any way of, like, you wouldn't be able to fuse anything practically. But, you know, that's not really a priority. So I can understand why, like, oh yeah, from a design perspective, this is super convenient. You just don't have to think about where you're pulling your power from. There's just one issue. You now have 6 pins where, like, there's no, you know, like, guarantee that the pins are actually properly connected. And under most circumstances, this won't cause issues, right? But the other issue, like, but the thing with the 8 pin power connector is like if you plug one of these in wrong, right? Like if these 2 pins are not plugged in, you're only getting a 3x overload. Whereas with the 12-volt high power connector, which incidentally looks like power, 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 ground, 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 and then you have like freaking 4 sense pins that don't actually do anything useful. So if 5 of these go missing, the connector melts, right? Which is like, because you get a 6x overload, whereas here you only get a 3x overload. Now, funnily enough, I have actually seen some tests of like intentionally, Yeah, I think I've seen somebody test that where they intentionally sent all the power through just one pin, and it still didn't manage to melt. So the connector does have some safety margin in it. It's not quite as borderline as a lot of people make it out to be, but at the same time, it's kind of ridiculous that it melts so much, right? Like, and I'm also not a fan of the fact that like it makes like it's not impossible to fuse a 12-volt high power connector like Sapphire's 9070 XT does, um, but NVIDIA cards don't because NVIDIA is just yeah. Um, well, um, anyway, so there, that's like a bunch of rambling about how, power connectors get balanced on GPUs. And the thing is, it can be completely passive. It doesn't require any active componentry. It just requires wiring up the card to be relatively balanced from the factory. And then you don't need to do anything past that point, right? So, yeah, hopefully you found this video somewhat interesting, if not particularly useful. Big thank you to TechPowerUp for the PCB pictures that they have in their reviews. There will be links in the description. And yeah, that's it. If you'd like to support the channel, there are links in the description. If you check them out, that would be very much appreciated. And that's it. So thanks for watching, and goodbye.